Okay, when we study circular motion, we focused on uniform versus non-uniform circular motion. But when we look at energy, we actually look at two kinds of circular motion, and a little bit differently. We say circular motion, which is horizontal circle versus vertical circle. Horizontal circle versus vertical circle. Why do we do that? Well, if you look at a horizontal circle, say this is a horizontal circle. I may actually draw a little bit differently. Say I have a pendulum like this, and I swing it in a circle, this circle. So I have a bob here and something, but this thing is going in a horizontal circle. So this is the horizontal circle. So there's a angle here, which you can just, let's call it alpha. And this is an angle of, it makes a cone, and it's actually called conical pendulum. This thing is going in a circle here, although from the perspective it's kind of oval, but it is a circle. And you can say this is radius r, and if the length is L, then this triangle that you can see, you can use this triangle to see that R has to be L times what will be is you have L and this angle, so that's the opposite. So R has to be L times sine of alpha. That's right. It's going to be sine of alpha. So this will be related like that, and it's going to go in this way, turn around this way. At no point is getting a zero speed, and we can say I'm going in a uniform way, maybe uniform speed. It could be speed of here and keep getting more and more speed, so it could be non-uniform, but we'll just, for the simplicity, we are going to look at as if it's going in uniform speed. Well, here you can see there's no height change here, and because there's no height change, potential energy does not change. Gravitational potential energy does not change. All we have is this thing is just swinging it. Another thing that happens is, if you look at the tension here and the gravity here, now they are kind of, mg is kind of 90 degrees to this plane in which it's moving, so mg is perpendicular to the direction in which it's moving. What's not so clear to you maybe is this tension is also 90 degrees. So, they're not really, tension is not doing any work on the motion, mg is not doing any work on the motion. So the energy doesn't really increase. So it's got same kinetic energy, total energy remains the same. So total energy equal to kinetic energy only. So if this was going at speed v, is half mv square everywhere for uniform speed. So no force did any work. Well, vertical circle, a prime example is the plane pendulum. Or you can have like airplanes making a vertical circle like that. Airplane coming down and pulling up. Plane pendulum is a simple enough system, and so let's look at it. I didn't draw it full, so let's draw it a little bit better diagram like that. So let's see. So this time the motion is all in this plane. Is here the motion was not in one plane. Here the motion is all in this plane. So if this is XY plane, then motion all in XY plane. If you look at it, over here, it's, say I let go here at v equal to 0. Then the speed will pick up and become very large, and then slow down and then stop, and then so these are then it's going to pick up again and just going to repeat. So v equal to 0. So this is a turning point, and this is another turning point. So if you see at any point, say it's this point, the velocity or displacement is in that direction, the velocity is in that tangent to that, and the tension force is that way. So tension force is always perpendicular to velocity. So tension force, just like over there, tension force is perpendicular to velocity. That means tension force will do no work. You remember that work between a force is a force dot delta r, right? This displacement if you divide by delta t. So force and velocity, if they are 90 degrees, this dot product will give you 0. So so this is the work. In work will be this, and divided by delta t will give you power. So the velocity and delta r are in the same direction. Okay, now that we said tension doesn't do work, only other force is mg. So the mg is a force that's a conservative force. So the work by mg we take into account using potential energy. So if I look at point A, point B, and point C, at A, kinetic energy is 0. So the energy at A is just potential energy at A. At B, well, B is the lowest point, so we can say potential energy is 0 here. So at B, and these are gravitational potential energy, and although we're not going to write that just to be simple. At B, potential energy at B is 0. So energy at B is all kinetic energy at B. And since tension is the only other force not doing any work, you have energy conserved. So energy at A equals to energy at B. So kinetic energy at B equals to potential energy at A. This is our fundamental observation here. So let's see if I have if I have this as theta, this is theta, big theta, this theta, the biggest one, angle theta, and the length is that. Then if I can figure out this height, then I will know the potential energy at A. How do I figure this height? Well, if I can figure that part out, then I can subtract this to get that. And you can see that this part, so we have this kind of situation. We need to figure this out, given this and given theta, and then subtract this from this whole thing. The whole thing is L. And this little part is adjacent, so it is L cosine theta. So L minus L cosine theta is this is the height we want. So KB will be half mvb square, and this will just be mg, and this is the HA, and HA is simply L minus L cosine theta. So it's mg L 1 minus cosine theta, taking L common from this. So if I divide out mass from both sides, I get Vb square equal to 2 times GL 1 minus cosine theta. So, and Vb is speed, so if I take a square root, I don't need to keep negative. So square root of 2GL 1 minus cosine theta. So if you tell me how big a string you have, at what angle you let go, I can tell you what's gonna the speed at the bottom part. As a matter of fact, I can apply this to any other place, right? So maybe I will do an example in next video where I will study pendulum having a speed at different points. Next continue this.